Welcome back. In our previous lecture, we were discussing combinatorial materials processing, and therefore, after discussing combinatorial materials processing, we move on to the next logical segment, which is looking at high throughput characterization. If you are doing combinatorial materials processing, chances are you are generating a large number of samples, or maybe even if you are making a single sample, you have got a nice gradient of compositions or crystal structures, and there's definitely going to be some sort of a gradient in terms of the physical properties. So how do you actually test this, or how do you actually characterize this? This is where doing high throughput material characterization comes into the picture. So just to give you a bit of a overview of what high throughput materials characterization or HTMC could look like, the main motivation for doing this type of work is to accelerate materials discovery, and as I mentioned, this is best used when you are using it in tandem with combinatorial materials processing and materials informatics. So by doing this type of high throughput characterization, you are actually ensuring that you are generating a large volume of data from the combinatorially processed materials. Now, it's not necessary that you always do high throughput characterization only with the samples that have been produced using a combinatorial type of methods. Sometimes even with a regular sample, a near equilibrium sample, there's a lot of information that can be extracted. So for example, if I am looking at a fairly complex alloy system and then I want to see its behavior with temperature, then what I would do is a bunch of in situ experiments and then collect the data from those in situ experiments. You might see that different parts of the microstructures are undergoing different phase transformation depending on what the local chemistry is, what the orientation relation between the different phases are, and so on and so forth. So if you are able to collect this entire spectrum of information, then that is basically something that would come and be considered as a high throughput characterization method. So just to give you an example with our good old X-ray diffraction, if you look at the early days of laboratory X-ray diffraction work, let's say sometimes in 1940s, 50s, 60s, you had a relatively crude system. The collection of the diffraction data back then was not a trivial task. It was quite manual and it was quite laborious, and the operator would actually have to manually set the goniometer angles and everything. So there was a huge amount of human intervention that was needed back then. With time, as computers became more and more affordable, people started coming up with this X-ray diffractometers, which could be controlled using a computer. So this cut down the laboriousness of the process. This meant that collecting the data became much simpler and you did not have to be extremely skilled in order to collect the data. Fast forward a little bit more. Nowadays, we have got X-ray diffractometers which have got stacks like this. So these stacks are stacks of sample changes. You will see that you've got the small shelves over here. Each of these shelves are holding one silicon wafer, for instance, if you're putting your powder sample on the silicon wafer. And then what you basically do is you program how many samples are there, and then this stack of shelves will slowly move upwards, and then with every run being completed, you will have a shift of this sample back to the empty shelf and the next shelf's sample getting shifted to this stage over here. So from rather relatively crude measurements with a lot of manual intervention, we advanced to computer controlled diffractometers, and then we got into a situation where we have got this robotic type of automatic sample changes. So the instrumentation with the X-ray diffractometers has evolved quite a bit, and as we move into the 21st century, we now have automated data collection when it comes to the X-ray diffractometers. This is what makes this type of techniques quite useful for high throughput materials characterization. So just to give you an idea over here, in this paper, the researchers were doing synchrotron studies. So when you are doing a synchrotron study, you are essentially doing a high flux and sometimes even a high energy X-ray diffraction experiment. So what they have done over here is they have taken a thin film which has been made in a very combinatorial manner, In other words, you have got a concentration gradient as you go from one side of the thin film to the other. Now, when you have a thin film like this, you can now start defining different angles. So you have got this angle, which is essentially your takeoff angle right over here. You have got the 2 theta angle, and then you have the detector on which the data is being collected right over here. So what you essentially do, you collect the data in a transmission mode, and that's why you get to see this rings like this from your sample. Collecting the data in transmission mode means it is a very quick process. It's almost a snapshot that you are collecting, and then you are trying to ensure that you get the diffracted beam from a slightly different part of your sample. So as a result of that, when you have a compositionally graded sample, by moving your stage and successively collecting the data, you are able to perform a combinatorial experiment. The figure on the right is another example where you are using synchrotron radiation in order to perform combinatorial experiments. Here what we have done is we have taken this hafnium-nickel 50-50 composition, and then we have heated it to fairly high temperatures. After that, as we are heating, we are collecting the X-ray diffraction data simultaneously, and as with the previous experiment, all of this data collection is being done in transmission mode, and therefore it's only a very short interval of time in which we are collecting the data, and that allows us to have fairly good resolution in terms of time as far as our data is concerned. Now, if you look at this experiment, again what we are doing is on the x-axis we have plotted the values in Q space, and in the y-axis we are plotting the temperature. When you are looking at this peak, the brightness of this peak corresponds to the intensity of the peak, and then what you basically see is at a certain temperature one set of peaks starts to disappear and another set of peaks starts to appear. So this is really where the hafnium-nickel intermetallic is undergoing a phase transformation. So this type of data collection again allows you to perform one single experiment where you are taking your sample and you are heating it and you are cooling it, and by collecting the data from that single experiment you are actually able to get the data at different temperatures. So this is how you are performing a combinatorial experiments, or you are doing a high throughput characterization using X-ray diffraction. Now, X-rays are not the only way in which you can do high throughput characterization. X-rays are quite common, but then you can do high throughput spectroscopy. One can do automated electron microscopy or even optical microscopy. One can do instrumented testing, where you can program a hardness tester or a nano indenter to make measurements from different spatial locations of your sample. So if you now have a sample which has got a composition gradient, in other words, if you have used a combinatorial processing method and then you couple that with this instrumented testing, you can now start getting the mechanical properties from different composition space in your sample. In order to do this type of high throughput materials characterization, there are certain experimental platforms that turn out to be quite useful. For instance, the figure on the left is what shows you a multi-sample holder for a scanning electron microscope. As you can see, in one shot you are actually inserting a lot of samples, and therefore you can study many samples without having to break the vacuum, without having to insert multiple samples multiple times. So this type of things becomes really useful, especially if you have an autonomous microscope where you can actually program the data acquisition such that you basically give the coordinates and you set up a recipe that there is a certain magnification that you want. You set up the focusing, and then in an automated manner the microscope will scan across a sample and start collecting the data. So this type of multi-sample carousels are quite common nowadays in scanning electron microscopes. You could even look at other methods like maybe a NMR type of technique where you have automatic sample changing. So essentially what happens is there is a robotic sample handler, and then what that does is it simply keeps on changing the samples in a programmed manner at the end of each run. In addition to autonomous microscopy and multi-sample holders and robotic sample handling, there are options in which you can have programmable stages where the stage can move in certain manner. And then once you use this type of techniques, what you really need is some sort of a automated data handling pipeline. So this part becomes really important because when you are doing this type of high throughput characterization, you end up acquiring a huge volume of data. And when you collect a huge volume of data, analyzing the data, ensuring that the data is structured properly, that becomes a big challenge. Another thing I want to talk about is in situ characterization options. So here what you see is a hutch inside a light source. Basically this is a synchrotron experiment being run, and what you see over here is the controller for a furnace, and right over here is where the furnace is located, and this is an induction melting furnace. If I blow up this part, what you will notice is I have got this induction unit over here. This hollow rod is an Inconel susceptor, and then the beam is actually coming in this direction. Alright. So what that basically means is when you look at this part right over here, this is where you have the detector. The beam is coming out from this direction, going through the sample over here, and then hitting the detector in this position. So this type of setups are quite common in synchrotron sources, where you essentially custom design the process condition and then collect the X-ray diffraction data simultaneously. In addition to synchrotron, the modern TMs are also well equipped for doing in situ characterization. Nowadays you have a variety of TM holders. The old-fashioned holders used to be a single tilt or a double tilt holder, but nowadays you have lots of other types of holders. So for instance, people who do catalysis, they often work with holders where you can have an in situ flow of a liquid. So those are called liquid cell holders for the TM. Other holders which are used for doing in situ experiments are something which might be having a MEMS chip in there, and then the idea over here is you are having MEMS heating, so you can study the phase transformations in situ in a TM. Similarly, if you want to do the experiments in a certain atmosphere, you have got those gas cell holders where you can actually have a gas inlet and a gas outlet to do the experiments in a controlled manner. Now, using those holders themselves can get pretty complicated, but they do provide you with the option of getting valuable in situ data. Similar to TEMs, you can also have in situ holders for SEM. So for instance, the one shown over here is a holder which is equipped with a heating unit, and then it has got a motor. So essentially what happens is you take the sample, you use these clamps, you fix the sample over here, and then you have a motor which is going to pull it. So as the motor is pulling it, it is applying a certain amount of force, and essentially what you end up doing is perform a tensile test inside the SEM. Now if you also have a heater in your stage, that means you are actually doing a high temperature tensile test in SEM, and then you are studying the deformation in situ in the SEM even as you are looking at it. As we mentioned, you have a variety of in situ TM holders. So the hot stage is one of them, the liquid cell is another one. People also have devised holders where you can apply some sort of biasing fields in order to look at materials like, for instance, ferroelectrics in an in situ manner. We have been talking also about in situ heating experiments in the synchrotron. So I just want to show you how the setup would look. So you have this type of furnace. This is like a very slim furnace that you've got, and right here you have got a cavity in the furnace which is basically this cavity, and then you have got a place in which you can put your sample, and around that you have got this very tiny heating elements, and as you put your sample over here, you will have to close this furnace and then put it in the beamline and program the furnace in order to heat up at a certain rate, and you will again be collecting your data. So once you collect your data, you would be able to get this type of data where on one axis you have got the value of Q, or you can convert it into 2 theta if you want. On the other axis you have got the temperature, and then in the third axis you have got the peak intensity. So this is how you would visualize the results of this type of in situ experiments. Now, when you are performing combinatorial experiments and you are doing high throughput characterization, what happens is you generate a huge volume of data. And so a major challenge when you are doing experimentation like this is how do you handle and manage the data. Specifically, you will face challenges with respect to the overall volume of the data, how diverse the data is, and how heterogeneous the data is. So how do you actually address this challenge? This is actually a major issue that one needs to look at while performing this type of high throughput experiments. So each time you are doing a high throughput material characterization experiment, you are likely to produce data which is of the order of at least some gigabytes and in some cases even terabytes. So you might easily generate data of the magnitude of 1 to 2 terabyte when you are doing 3 to 4 days of this type of very intensive high throughput material characterization experiments. So managing and analyzing this huge volume of data is going to be a major challenge. And so how do we actually go about it and what are the challenges we are facing? So we talked about the volume of the data, then let's talk about the diversity of the data. So for instance, the type of data you are looking at could be some sort of a spectra. So you have got a spectra that looks like this. The first problem you see over here is that your peak is asymmetric. So what you would have to do is you would have to deconvolute the peak and you would find that there are actually two peaks which are very close to each other, having some amount of overlap, which might end up giving you a peak like this. So when you are looking at the type of data, you might be having a spectroscopy data, and within the spectroscopy data, you will be having this challenge of deconvolution of the peaks. Or you might be even looking at diffraction data, where you have got this pretty nice diffraction pattern, but then if there are in situ experiments being done, then in one direction, this diffraction patterns are definitely going to change. So as you are maybe applying load or maybe when you are applying temperature along that axis, the diffraction data is going to change. So how do you capture that? And even when you are looking at diffraction data, what you see is the peak positions have not changed, but then the relative intensities of the peaks are quite different. So one might be a textured sample, one might not be a textured sample. So it's not just the peak positions which will characterize this. So how do you capture the features from data like this? That is going to be really, really critical. In addition to spectroscopy or X-ray diffraction type of data set, you might also be doing TM analysis, and if you are doing TM diffraction, then again you have this challenge that you might end up capturing lots of different diffraction data. As you are collecting the diffraction data, you would be collecting them along certain zone axis, and you would be changing the zone axis as you are collecting the data, right? So even for a single material and maybe even a single phase inside a multi-phase single material, you will be collecting lots and lots of TM data with slightly different information being captured in there. You can even have data in the form of images. So for instance, this is a SEM image from one of our works which shows beautiful dendritic growth. So how do you actually deal with image data like this? More to the point, when you are doing a fairly extensive characterization of material, of a single material, you might be simultaneously getting spectroscopic data from your sample, you might be collecting the X-ray diffraction data, you might be collecting the TM data, and then you might also be collecting the SEM data. And you have to find a way of working with this diverse set of data and ensure that it all makes sense. In other words, that the data are somehow talking to each other. You don't want a situation where you are not able to correlate one type of data with the other type of data. So this type of diversity in the data that you are collecting by performing not one but multiple different types of high throughput material characterization experiments is going to bring forward another challenge when you are trying to do data management from these experiments. Then of course, there is the challenge of heterogeneity. So what do I mean by that? If your data is heterogeneous, maybe your sample is also heterogeneous, so maybe different parts of the samples are not behaving in the same way. So when you collect data from a very heterogeneous sample and you find that being captured in the data, you really need to have accurate spatial and temporal resolution in your data in order to make sense of all of it. So this is not a trivial challenge, and this is something that people actively look to sort out in a variety of experiments. So for instance, if you have heard of atom probe tomography, that is an experiment in which the volume of data you are collecting is huge. Essentially what you are doing is you are trying to pinpoint the position of atoms of different elements. So there's a huge wealth of data that is available, and then it is something which is very ripe for doing a materials informatics type of analysis in order to make sense of that data. When you have data which is this large and this heterogeneous and this diverse, sometimes it makes sense to come up with some sort of a automated data processing and analysis recipe. So what do I mean by this? The first step over here is performing your high throughput experiment. And let's take an example. Let us say that we are talking about an in situ synchrotron diffraction experiment where the in situ data is being collected when your sample is being heated. So the first step is to perform the experiment itself, and when you are performing the experiment, you have to ensure that you are acquiring the data. So data acquisition is another thing that you have to understand. But data acquisition in this case is being done by the detector which is being used in the synchrotron source. After that, you have to figure out that this entire process is being controlled through a computer, where maybe you have some form of a computer language which is controlling the translation of the stage, maybe even the motion of the detector, because you can bring the detector closer to your sample or take it further away, and that allows you to either expand or collapse the reciprocal space. So there's a ton of different variables that can be possible, and you might actually employ multiple of those options when you are doing the data acquisition. And then as you are doing the data acquisition, this entire process is being collected by some sort of a script which is being used to control the instrumentation part. In this specific example, you might think that the data is being collected as images because you have got this maybe a CCD camera at the end which is acting like your detector. Once you have acquired the data, the next step is to do some sort of data pre-processing. The raw data files that you get directly from the detector are not really usable. So you have to do some sort of pre-processing to convert the raw data into a usable data. So maybe you do this by loading it into the GSAS2 software, and with the GSAS2 software now you can start taking this detected data and converting that into images, and after you convert that to images, you can set up an automated recipe. You can create a macro where when you are getting this diffraction rings, you can actually integrate over the all of the angles, and you can convert this diffraction rings into this type of much more easily understandable X-ray data. So there is a good amount of pre-processing that can be done. Nowadays, there are a bunch of different softwares. So GSAS is one which is quite useful for X-ray diffraction, and the reason I'm mentioning that is because it's a free software. Anyone can go to the GSAS website and download it. So this type of softwares also gives you the option of writing a macro. So once you write a macro, you can actually create a data processing, or rather a data pre-processing pipeline with which you now start building up your final data set. So as you are building up the final data set, you need to find a way of storing the data. So whether you want to store it as an Excel file or a CSV file or any other file format, that is up to you. But the bottom line is you have to find a way of efficiently storing the data. So once you have figured out how you are storing the data, the next thing is to retrieve the data when needed and do the type of analysis that you really want to do. So for example, in this case, maybe the type of analysis we want to do is a read-file refinement. Now you will be collecting lots and lots of data as a function of time and temperature, and therefore there's a large number of read-file refinement that has to be done. So once again, you can use this GSAS software and set up a sequential read-file refinement where you sort of automate the process by creating a macro once again. After you have done the data analysis, now it is time for data visualization and then looking through the results a little bit more carefully. So this is again something that you can do by leveraging whatever was covered in the earlier lectures by Professor Biswas when he was talking about data visualization. So you have to find a suitable way of representing the data or visualizing the data in a manner that makes the most sense to you. Now, of course, within this process, there is the opportunity when you have done the data pre-processing to see if you can actually start extracting some key features if you want to couple this process directly with materials informatics. So this feature extraction part can get inserted right after data pre-processing.
And then as you do the feature extraction and feature calculation, then that becomes the interim step when you go from data pre-processing to data storage. So this is by and large a fairly generic workflow for doing some form of a automated data processing from high throughput experiments. Now, one thing I need to stress is that when you are performing this type of experiments, these are not easy or trivial experiments to do. And therefore, the data that you are getting out of it is actually quite priceless. It is really important that you store the data properly and make it accessible. So in that sense, the databases must be structured in a fair manner, and fair over here stands for findable, accessible, interoperable, and reusable. So just to give you an example, the materials project is something which actually follows this fair data principle. Other than that, you can also find other databases like Nomad. This is something again that we have talked about, which follows this fair principle of data management. So when we say data should be findable, the first thing that comes to the mind is you should be able to find different data points as and when that is needed. And what that means is the labeling and the indexing of the data has to be very systematic. There has to be certain rules with which you are indexing the data. And so the idea over here is if the rules are well set, then the user can write a proper query in order to retrieve that data. So proper indexing of data sets would be very important. Availability of any metadata which is associated with your process data, that would also be very useful. And then your data, of course, has to be easy to locate. Next comes the accessible part. And so when we talk about the data being accessible, what we really mean is the data retrieval process and access must be quite easy. What that would require is sometimes creating permissions. So it may so happen that when you are creating a database, you might be also having some proprietary information in there. And so the permissions have to be set up in such a way that people who have the permission to access the proprietary data will be able to do that. For all other people, you would have some amount of security for the proprietary data. Data being interoperable is also very important because chances are you will have to integrate the data. As we have discussed, you might be having one sample from where you are getting spectroscopy data, microscopy data, and so on. You have to ensure a way of integrating data from all of these different types of characterization methods or different types of platforms. And therefore, it's always good that if you can keep your data in some standard formats so that the data can talk to each other, you should be able to pull the data into a common data set in order to do the subsequent materials informatics. So this data being able to talk to each other is also very important. And finally, you want that the data should be reusable. So having the data which is reusable means this is robust data. This is something which will reduce the redundancy going forward. This ensures that the work that you have done is done in a very fair and transparent manner, and then the data that you have got is reproducible. In other words, the data that you are generating and the way you are storing it ensures that you are making a genuine scientific contribution over here. Now, of course, there are lots of nuances associated with doing high throughput materials characterization. And for that, you have to understand the individual characterization technique very well. You have to understand the associated instrumentation part very well. In this course, so it is beyond the scope of this course to go into details for the instrumentation parts or the individual characterization techniques part. But hopefully, this lecture has provided you with a useful overview of what different types of high throughput materials characterization techniques can be and how you want to deal with the data that you are acquiring from those materials characterization techniques. So with that, we are going to stop over here. Thank you for joining, and next time we are going to talk about synthetic data.